Hello and welcome back. We look at a few more problems on thermodynamics. So the problem here says there is a rigid container which contains 1.2 kg of argon, which has a molecular weight of 40 kg per kilomole. Cv, the specific heat at constant volume, is 392 joule per kg Kelvin at 300 Kelvin, and the gas is at 101 kilopascal. There is another tank which contains 1 kg of O2, whose molar mass or molecular weight is essentially 32 kg per kilomole. Its specific heat is given and the conditions of this gas are given. The tanks are connected by a pipe with a valve. So, we can think of it as something like this. So, we have one tank containing argon, we have another tank containing oxygen. The conditions of each are known and they are connected by a valve here, and the valve is opened and the gases are allowed to mix, and after they mix the final temperature is given. We are asked to determine the volume of each tank, the final pressure and heat interaction. We are told that we can use an ideal gas model. So, let us sketch this in a form which is useful to us. So, we have argon and we have oxygen. We have a valve. So, we are going to write down all the information we have. We have 1.2 kg of argon, 1 kg of oxygen. So, there is 1.2 kg of argon at 300 Kelvin and 101 kilopascal. And we have oxygen. We have 1 kg oxygen at 400 Kelvin and 500 kilopascal. So, this is what we have. The properties of argon and oxygen are given. So, the molecular weight of argon is 40, Cv is 392. Joule per kg Kelvin, and molecular weight is 40 kg per kilomole. For oxygen, this is 32, and we have the Cv of oxygen given as 696 Kelvin, joule per. What we are told is that after these two mix, the final temperature is 360 Kelvin. So, after they mix, they come to a common temperature of 360 Kelvin. So, this is essentially what we see. So, what we want to find out is the volume of each tank, the final pressure and the heat interaction. So, we want the volume of each, the final pressure and any heat transferred. So, we have here two ideal gases, each of which is in a tank initially. We know the initial mass, we know the initial temperature, we know the initial pressure. So, we can find out the volume of each tank. Let me call this as say tank A and B. So, we can find out the volume of each tank by using the first law. So, that is something which we can do, by using the ideal gas relationship. So, that is something we can do. So, we have for an ideal gas PV is equal to mRT, where R is the specific gas constant given as R bar by M. So, this is something which we have. So, we know over here in both cases the mass. So, we know this, we know the temperature, we know the initial pressures. We do not know R directly, but we do have the value of Cv and we have the value of molecular weight. So, we can find out R because it is R bar by M. So, we can find out the volumes of each of these. So, the volume of argon is essentially mass of argon into R into T by P. Instead of R, I am going to use R bar by M, all of these for argon. So, that is 1.2 into A314.5, it is at 300 Kelvin. The pressure is 101 kilopascal, that is 101 10 to the power 3 Pascal, and the molecular weight is 40. So, this should give me the initial volume of argon, which I am calling as the volume of the tank A. Similarly, I can find out the volume of oxygen initially, that is 1 kg into A314.5 joule per kg Kelvin into the initial temperature, which is 400. The initial pressure is 500 kilopascal, that is 510 per 3 pascals, and the molecular weight is 32 kg per kilomole. So, this is VO2 initially. I am calling it as the volume of tank B, and I can find out these values, which is what I am going to do. So, I get this as 0.74 meter cube, and I get the other one as 0.207 meter cube. So, I have the values for the volumes of the two tanks. So, we have found the volumes of the two tanks. So, the initial volume is there. So, what we also want to find out is the final pressure and any heat transfer. So, what we can do is we can consider both of these gases together as our system. So, once we open the valve, we see that the oxygen is at a high pressure of 5 bar, 500 kilopascal. The argon is at a lower pressure of 1.01 bar, which is 101 kilopascal. We expect that the oxygen will flow from here into this tank, and it will mix, and then some of this argon will diffuse back and it will mix. If we leave it for a long enough time, we will have both of the tanks containing a mixture of oxygen and argon, and they will be at the same pressure. So, what we are going to do is consider our system to be both the argon and the oxygen. So, both tanks A and tank B. So, we have initially these conditions. So, finally, we are going to have a mass which is both of them together. The final mass is the mass of tank A plus tank B, that is 1.2 plus 1. I will have a mass of this quantity. I do not know what the final temperature is going to be. I do not know what the final pressure is going to be, but what I do know is the final volume is the volume of both the tanks. So, that is going to be 0.74 meter cube plus 0.207 meter cube, which is essentially 0.947 meter cube. So, I know this as well, and what I do know is that if I consider both the tanks as a system, there is transfer of mass between two parts of the same system. There is no transfer of mass between anywhere else. The tanks themselves are rigid. Anything which is flowing between these two is internal to the system. So, there is no work interaction between these two tanks and the surroundings. So, what I also know is that any work interaction is 0. There is no shaft work, there is no electrical or mechanical work. So, what I know is that there is no work interaction. So, that I know is 0. What I know is there can be heat transfer and correspondingly a change in internal energy. So, if I was to write the first law for this system, the first law in considering only internal energy, because there is no change in potential or kinetic energy, the system is not moving. So, I would have dE, which I can replace by du, is del q minus del w, or I have delta u is essentially this, and I also know that this is going to be 0. So, I have delta U is essentially 1 Q2. So, I am supposed to find out the heat transferred. If I find out delta U, that should be sufficient. What I also know is that the temperature finally, this is given to me, the final temperature is 360 Kelvin. So, if I now consider the final mixture, I have a mixture of argon and oxygen. So, for that mixture, the ideal gas relation will still hold. This is still true. I do not know the final pressure. I do know the final volume. I know the final temperature is given to me. I know the final mass. I can find out the specific gas constant of this mixture because I know the constituents. So, I should be able to find out the final pressure. So, that is something which I am going to do now. So, what I will do is find out the gas constant. So, this would be essentially the universal gas constant divided by the molecular weight of the mixture, which I am calling as M2. Now, for the molecular weight of the mixture, what I know is, or let me just call it mixture itself. I know that this is 1 by sigma of yi by mi. So, I need to find out mass fractions and I know the individual molecular weights, which means I can find out the molecular weight of the mixture. So, let me find out those. So, I have the mass fraction of oxygen is mass of oxygen by total mass. So, the mass of oxygen is 1 kg. Total mass is 1 plus 1.2, which is 2.2 kg. The mass fraction of argon is mass of argon divided by total mass, or it is also 1 minus this, both are the same. So, I can find out these values. So, this comes out to be 0.454 and this comes out to be 0.545. So, I know these. So, I can now find out the molecular weight of the mixture. This is yi by mi sigma. So, this is 0.454 divided by the molecular weight of oxygen is 32 plus 0.545 divided molecular weight of oxygen, which is 40. Which gives me a total molecular weight of 35.95 kg per kilomole. So, I can now put these into the ideal gas relation. So, I have P2, V2 is MR2T2. I want P2. So, that is M2R2T2 divided by V2. So, M2 is 2.2 kg, R2 is 8314.5 divided by the molecular weight, which we just found out. I know T2, it was initially as 360 Kelvin and the volume is here. We found out the individual volumes and summed them up, that is 0.947. So, I can now find out this. Which comes out to be 193.4 kilopascal or essentially 1.93 bar. So, what we see is that we had argon which had a pressure of close to 1 bar, we had oxygen, we had more argon, less oxygen had a pressure of about 5 bar. When we mix it, we have a pressure of about 2 bar. The volume fractions are different, the mass fractions are different, so we get some value which lies between these two, but not exactly halfway in between the two. So, this is what we get. What we are also asked to find out is the heat transferred. So, the heat transferred we know already it is equal to delta U from the first law. So, what we need is delta U. So, we need 1 Q2 which is equal to delta U. Now, this delta U I can split it as the mass of the argon into delta U of argon plus the mass of the oxygen into delta U of oxygen. So, that is mass of argon into CV of argon into T2 minus T1 for argon and similarly for O2. So, the mass of the argon which I had is 1.2 kg, it was initially at 300 Kelvin, CV was 392 joule per kg Kelvin, T2 the mixture temperature is 360 and this was initially 300. I had 1 kg of oxygen whose CV was 696 joule per kg Kelvin, whose initial temperature was 400 and final temperature is 360. So, we can calculate this. Which gives us a value of 56 kilojoule. So, what we see is 1 Q2 is positive. Our notation is that if 1 Q2 is positive, it means heat is being added to the system. So, there must be something else outside, maybe the outside surroundings are hotter, because of which there is heat being transferred into the system consisting of both A and B when this process is happening. So, an amount of 56 kilojoules was added to this. There is no work interaction in this case, both the tanks are rigid, there is heat being transferred to it while this mixing process is going on. And finally, we see that the internal energy of the argon and oxygen mixture has gone up during this process. So, we wanted to find out the final volume, which we did because it is the same as individual volumes added up. We wanted final pressure, which we did using the ideal gas law, and we wanted to find out heat interaction, which we did by using the first law and finding out delta U for the ideal gas mixture.